Welcome back to this next video in which we are discussing the parathyroid glands and vitamin D. Okay, so we've discussed that when the free calcium concentration in the blood goes too low, that's what is going to trigger the chief cells of the parathyroid gland to release parathyroid hormone. And parathyroid hormone is going to act on the kidneys, the bone, and indirectly through vitamin D on the gastrointestinal tract. We'll talk about that. You will understand what I mean by that by the end of the video, to bring calcium back up. Okay, so we're now going to discuss the mechanisms underlying these actions in much more detail. So we're going to begin with the kidneys. So, firstly, let me just give you a reminder of the structure of the nephron and the basic principle of how the kidneys work, and then we'll actually talk about calcium resorption in the kidneys, and also about phosphate resorption in the kidneys, and what parathyroid hormone is actually going to do to these. Then what we'll talk about is how parathyroid hormone is going to trigger the final stage of the production of 1,25-dihydroxy vitamin D, which is going to occur in the kidneys. So we'll have to have a big diversion off to talk about vitamin D for a while, and then we'll see how parathyroid hormone triggers the last stage in the production of the active form of vitamin D, and then we'll see how the active form of vitamin D and parathyroid hormone are then going to act together on the bone, and how vitamin D is then going to act on the gastrointestinal tract to cause the remaining actions that I've listed here. Okay, so the kidneys though first. So let me draw out a simple picture, a simple cartoon then of a nephron. So a nephron, first portion of the nephron is Bowman's capsule here, okay, which I'll show like so. And of course what's in this space is going to be the glomerulus, made up of loads and loads of capillaries, and the principle is that fluid from the blood is going to filter from the glomerulus into Bowman's capsule here, the first portion of the nephron. Okay, so this, I will label this up as Bowman's capsule. So this is going to receive the glomerular filtrate. So this is Bowman's capsule. I think I'll actually colour it in, colour code the different portions in. So we'll have Bowman's capsule shown here in red. Okay, so the glomerular filtrate has arrived, and pretty much it's very similar to the blood serum. So it's well, firstly, what is meant by blood serum? Remember, the blood consists of the fluid and the cells. The blood plasma means the fluid of the blood, i.e. without the blood cells. So if you get rid of all the blood cells, what you've got left is called the blood plasma. Then blood serum is one step up from that. Blood serum is when you've removed all of the plasma proteins. So there's loads and loads of massive great molecules flying around in the fluid of the blood, and these are the proteins that are mainly put into the blood by the liver. Okay, if you remove all of those and you're just left with all of the tiny molecules that make up the blood fluid, the blood plasma, that is what is meant by the blood serum. So the glomerular filtrate is very similar to the blood serum. Most of the tiny little molecules of the blood fluid are going to be filtered into Bowman's capsule, and they're going to make the glomerular filtrate. Now, a lot of what's in there, a lot of what's initially in the glomerular filtrate, we do not want to chuck into the urine. So the next step is now to resorb loads of the stuff in here, and then just leave in the bits that we do actually want to excrete, and that will become the urine. So the length of a nephron is now all about reabsorbing the portions of the glomerular filtrate that we want to keep, and then leaving the bits that we don't in to actually become the urine. And also the nephron does secrete things into the fluid as well that we want to get rid of from the body. Okay, so the different portions of the nephron then. So the first portion of the nephron is of course the proximal convoluted tubule, which would be quite long, but just for lack of space I'll just show it here. So this is called the proximal convoluted tubule, the PCT for short, okay, and I'll write its full name out here. So proximal means near the beginning, okay, or near the start. Convoluted is what C is for, and that's a word that means that it twists around, so I've tried to show it twisting here. So proximal convoluted, oh wait, how am I doing this? No, it should be convoluted. convoluted, like so. Okay, and then it's tubule. I'll try and squeeze this in here. So proximal convoluted tubule, and then the proximal convoluted tubule ducts down. So we now have the loop of Henle following the proximal convoluted tubule, and the loop of Henle, remember, ducts down into a lower portion of the kidney. Okay, so all of the portion that we've talked about so far, Bowman's capsule and the proximal convoluted tubule, they are in the cortical portion of the kidney, they're in the outer portion of the kidney. Whereas now the loop of Henle is going to duct down into the medullary, the middle portion of the kidney. So I'll just colour in the proximal convoluted tubule here in pink, like so. So this loop that the proximal convoluted tubule is going to flow into, the portion following the proximal convoluted tubule, this is going to be called the loop of Henle. Okay, and you have the descending portion of the loop of Henle, known as the descending limb of the loop of Henle, and then the ascending limb of the loop of Henle here. Okay, and then what's going to follow is what's called the distal convoluted tubule. But firstly, let's just discuss the different portions of the loop of Henle. Okay, so the entire loop here, all of this that's ducking down into the deeper portion of the kidney, into the medullary portion of the kidney, this is known as the loop of Henle, which is spelled like so. Okay, and it's split into different portions. The portion that's going down, the portion that's taking the fluid down into the deeper portion of the kidney tissue, the medullary portion of the kidney tissue, which I'm now colouring in yellow here, this is known as the descending limb of the loop of Henle. And so that I don't keep having to write out loop of Henle, I'll just abbreviate it down to LOH. Okay, so this yellow portion here, this is known as the descending limb of the loop of Henle. So I'll put limb of the LOH here. Okay, so if you hear people referring to the descending limb or the descending limb of the loop of Henle, it just means the portion of the loop of Henle that's actually going down into the medulla rather than the portion that's coming up. Okay, so the portion that's coming up then, you can hopefully guess what the name of that's going to be. It's going to be the ascending limb of the loop of Henle. But the ascending limb of the loop of Henle is split into two different portions. The bottom portion, which I'll colour in blue here, is known as the thin ascending limb of the loop of Henle. So this is called the thin ascending limb of the loop of Henle. And then the portion above that, the portion that's closer back up to the cortical portion of the kidney, that's called the thick ascending limb of the loop of Henle. So this is the thin ascending limb of the loop of Henle. And this one, I won't write it fully out again, but I'll just put that this is the thick portion. So this is the thick ascending limb of the loop of Henle, and this is this green portion here. So we divide the ascending limb of the loop of Henle up into the thin portion and the thick portion. Okay, following the loop of Henle then, what do you have? The final portion of the nephron is then the distal convoluted tubule, which again is a twisting tubule like so. Okay, now it's because it's further away from the Bowman's capsule, it's called the distal convoluted tubule, often abbreviated down to the DCT. So the D here is for distal, meaning far away, and then the distal convoluted tubule is going to drain into a collecting duct, a cortical collecting duct, because it will be up in the cortex, because remember, we're now up in the outer portion of the kidney because we've come back up in the ascending limb of the loop of Henle, so the distal convoluted tubule of the kidney is back up in the cortex. So initially we'll drain into a cortical collecting duct, but that cortical collecting duct will then go down through the medulla, so you'll have a medullary collecting duct, and then it will drain into the renal pelvis, and the fluid will then go down into the ureter and down into the bladder. Okay, so this portion here is then the collecting duct that the nephron is draining into. Okay, so now that we've got this picture, let me summarise again what the nephron is going to actually do. So we are getting glomerular filtrate coming into the Bowman's capsule, which is basically just like the blood serum. So the blood with the cells taken out and all the proteins taken out. Of course, we do not want that to be your urine. That is not urine, okay? We want to take loads of bits of that back. We don't want to just throw all of that away, okay? So then for the nephron is all about reabsorbing all of the bits that we want, and then also secreting in things that we don't want, and then the stuff that we chuck then into the collecting duct, which will drain down into the renal pelvis and then go down the ureter to the bladder, that's actually going to be urine. Okay, so calcium is going to be one of the key things that we reabsorb along the length of the nephron, and so is phosphate ions. So parathyroid hormone is going to work to affect the calcium reabsorption and the phosphate reabsorption along the kidney. So let's start by discussing calcium reabsorption along the length of the nephron, and then what we'll do is discuss phosphate reabsorption, and then we'll discuss how parathyroid hormone affects both of them. Okay, so firstly let's do calcium resorption in the kidney. So we're going to end up with a lot of calcium in the glomerular filtrate. We certainly do not want that to all go into the urine, so we have to reabsorb it along the length of the nephron. Where are the key sites of resorption of calcium along the nephron? Well, the key places where we reabsorb calcium along the length of the nephron are the proximal convoluted tubule, the thick ascending limb of the loop of Henle, and the distal convoluted tubule. So here, here, and here. Okay, so in percentages, the proximal convoluted tubule is the main place where we reabsorb calcium. 65% of the calcium ions in the glomerular filtrate are going to be reabsorbed into the bloodstream in the proximal convoluted tubule. So we're going to take 65% of the calcium ions that are in the glomerular filtrate out in the proximal convoluted tubule. Then in the thick ascending limb of the loop of Henle, which I'll just call the thick, okay, we are then going to resorb a further 25%. Okay, so 25% of the calcium that was in from the initial glomerular filtrate. So I don't mean 25% of what's left when it's arriving here. I mean 25% of the calcium that was in the initial glomerular filtrate is going to be reabsorbed in the thick ascending limb of the loop of Henle. Okay, so by the time it gets here, 90% of the calcium has been resorbed and only 10% is left over. Then finally, in the distal convoluted tubule, we generally resorb about 8% of the calcium that was in the initial glomerular filtrate, and that therefore leads to about 2% of the calcium in the glomerular filtrate actually remaining there and then going into the urine. Okay, we are going to raise the amount of calcium that we resorb so that pretty much none is going to then end up in the urine. So, what I now want to talk about is the actual mechanisms by which calcium can be resorbed across the renal tubule cells in the proximal convoluted tubule, the thick ascending limb of the loop of Henle, and the distal convoluted tubule. So let me draw some renal tubule cells then. So let's say this is a renal tubule cell, and of course it will have neighbouring renal tubule cells. So these tubes are lined by epithelial cells, and these epithelial cells will have two different faces. Okay, so they are two-faced cells. They have a face which faces the lumen, which is the apical face. Okay, so this side is facing into the lumen, and I'm a bit conscious that this picture is a little bit small, but never mind, I've done it now. And then they have a basolateral face, which I'll just abbreviate down to BL, but I suppose I should write it out at least once. So a basolateral face here. And these two faces are very, very different. They are not continuous with one another because of these things in between them. These are tight junctions. So these bits in red here, these are tight junctions, and they will join this renal tubule cell to the next renal tubule cell along. And although this is a two-dimensional picture and therefore these things look as though they're just little lines here, in reality if I was looking at the renal tubule epithelium, these would go all the way around the renal tubule cells. So let's say I was a little man standing in one of these tubes. What I would actually be seeing is that, say, here is a renal tubule cell, here's its neighbouring renal tubule cell, and then another one here. The tight junctions are going to fill in all the gaps. It's like it's often compared to that plastic packaging that they have around beer cans. Okay, so if you go to the supermarket and buy very cheap alcohol, then the beer cans can be attached to one another by this sort of plastic mesh that sort of goes around the top of the beer cans. That's what the tight junctions are often compared to. So in all of these gaps between the cells, you're going to have blockade, basically. You're going to have proteins blocking those gaps, and that's what is meant by tight junctions. Okay, so it's this thing that permeates all the spaces between the renal tubular cells, and therefore truly makes it so that the membrane of each of the renal tubular cells that faces into the lumen is separate from the membrane that faces the basolateral side, i.e. proteins that are in the apical membrane, they cannot just move into the basolateral membrane, because if I was a protein in the apical membrane, so remember I'm a little man standing looking at the apical membrane from within the tube. Okay, here is a protein in the cell membrane. It cannot move to the basolateral side of the cell membrane, because if it was to move over here, it would hit this tight junction here. It would hit a solid wall, and it cannot pass that. Okay, so this is a really important concept to understand, that these renal tubular cells can have different proteins in the apical membrane from the proteins that are in the basolateral membrane, and that's truly how they are capable of actually moving things from one side to the other side, having different proteins in these two different membrane faces. Okay, right, so here are my renal tubular cells then. So now we're talking about calcium resorption in these renal tubular cells. Okay, so there are two different ways that calcium can be resorbed across the renal epithelium. One is that it can go in a paracellular fashion, and the other is that it can go in a transcellular fashion. And actually the paracellular fashion is the main fashion in which calcium is reabsorbed in the proximal convoluted tubule, and it's a major way in which it's resorbed in the thick ascending limb of the loop of Henle. The transcellular route is more important in the distal convoluted tubule. So let me explain these two routes. So paracellular resorption of calcium, that means that the calcium doesn't actually have to go across the cells. Indeed, instead it goes parallel to the cells. It goes through the tight junctions. Now the tight junctions are very tight. They are good enough to stop proteins moving across them. But you know, a calcium ion is a very small thing. They're not quite that tight that they're not going to allow calcium ions and water molecules to move across them. So calcium ions can move across these tight junctions and go from the luminal side to the basolateral side. And indeed, in the proximal convoluted tubule, so we'll start with the proximal convoluted tubule here, 80% of the calcium that's reabsorbed, so all of the calcium that's resorbed in the proximal convoluted tubule, and we know 65% of the calcium ions in the initial glomerular filtrate are going to be resorbed in the proximal convoluted tubule. Of all of those calcium ions, 80% of them will cross in the paracellular route, i.e. they will cross through the tight junctions that surround the renal tubular cells. Now, why do these calcium ions move? Well, it's because there is a electrical potential difference across the renal tubule epithelium, especially in the proximal convoluted tubule. Calcium is a positively charged ion, so it wants to move to where the electrical potential is lower. Okay, so in the proximal convoluted tubule, across the epithelium of the proximal convoluted tubule, there is what is known as a transepithelial electrical potential difference. Okay, so there's going to be a voltage. So remember, a voltage is the same thing as an electrical potential difference. It means an a difference in the electrical potential between 2 points. So the electrical potential in the lumen isn't going to be the same as the electrical potential in the basolateral fluid here. Okay, and in fact the electrical potential is going to be lower in the basolateral fluid than it is in the luminal fluid. So the electrical potential in the luminal fluid is higher than in the basolateral fluid. This will give, it will produce a drive for calcium ions to move from the lumen to the basolateral fluid, and this is what's actually going to cause the calcium ions to move from the luminal fluid into the basolateral fluid across the tight junctions in this way. So in the proximal convoluted tubule and also in the thick ascending limb of the loop of Henle, there is an electrical potential difference across the epithelium of that tubule that has the electrical potential in the lumen being higher than the electrical potential in the basolateral fluid, and it is this that provides the driving force for calcium ions, which are a divalent positively charged ion, to move across the cell membrane, and it just goes, to move across the epithelium, not the cell membrane, and it just goes through the paracellular route across the tight junctions in this way. Now, of course, when calcium moves, water is going to have to follow by osmosis. So calcium and water molecules are going to move in this paracellular route. And this also occurs in the thick ascending limb of the loop of Henle, and approximately 50% of all the calcium ions that are resorbed in the thick ascending limb of the loop of Henle are going to be absorbed in the paracellular route. So it's a major way of resorbing calcium in both the proximal convoluted tubule and the thick ascending limb of the loop of Henle. Okay, it's not important in the distal convoluted tubule. So in the distal convoluted tubule, there isn't such a dramatic voltage across the cell membrane, and therefore there's not that drive for the calcium ion. Sorry, I keep saying cell membrane. There's not as dramatic a voltage across the epithelium of the renal tubule, and therefore there isn't the same drive for the calcium ions in the lumen of the distal convoluted tubule to cross the epithelium because of that electrical potential difference. So they're not going to move because of in this paracellular route. Okay, so let's now talk about the other way that calcium can be resorbed, which is the transcellular route. And in the transcellular route, trans means across, so this means that we're actually going to take the calcium across the cell rather than parallel to the cell. So in the proximal convoluted tubule, only 20% of the calcium that you resorb is going to go in the transcellular route. In the thick ascending limb of the loop of Henle, only 50% of it's going to go in the transcellular route. In the distal convoluted tubule, it's pretty much all going to go in the transcellular route. And it's this transcellular route that parathyroid hormone is actually going to be able to regulate. Parathyroid hormone doesn't have the ability to regulate how much calcium is being resorbed in the paracellular route, in the proximal convoluted tubule and the thick ascending limb of the loop of Henle. It does have the ability to regulate the transcellular absorption of calcium. Okay, so how is this transcellular absorption of calcium going to work? Well, we need to get the calcium ions in the lumen of the proximal convoluted tubule, or in the lumen of the thick ascending limb of the loop of Henle, or indeed in the lumen of the distal convoluted tubule, to firstly go into the cytoplasm of the cell, and then from the cytoplasm of the cell into the basolateral fluid here. So we need to get them across two membranes. Now, getting them across this membrane is absolutely easy, and the reason is, remember, calcium concentration inside cells is tiny. It's around 100 nanomolar. Tiny compared to the calcium concentrations we'll have in the extracellular fluid. So all we actually need to do to get a net movement of calcium from the lumen into the cytoplasm of a cell is give it a route to get across the cell membrane, give it an ion channel that it can move across the cell membrane through, and indeed that's what we're going to do in these cells. So on the apical membrane of our renal tubule cells, in the proximal convoluted tubule, the thick ascending limb of the loop of Henle, and the distal convoluted tubule, we are going to put ion channels for calcium. So these are going to be calcium channels. So in purple there, this is representing a calcium ion channel. And it is not a voltage-gated channel. It's not, its open state isn't determined by what the electrical potential difference across the cell membrane is doing. Its open probability, i.e. how likely at any one time it is to be open, is determined by other factors, okay, not the electrical potential difference across the cell membrane. Okay, so we have an apical calcium channel, and of course we're not just going to have one of them, even though I've drawn just one of them on this picture. We're going to have loads of them in the apical membrane. And this is where this concept of these two faces of the renal tubule cell being separate becomes important. These calcium channels that are open independent of the electrical potential difference across the cell membrane, these are going to be localized specifically in the apical membrane, not the basolateral membrane here. Okay, so what you're now going to get is calcium ions from the renal tubular fluid here, moving from the fluid into the intracellular fluid here. So here's how we're going to move calcium across the apical cell membrane. Now, of course, it becomes more of a problem because we want to move the calcium from the intracellular fluid here to the basolateral fluid, and then we're moving it up its concentration gradient. So what we're now going to have is active transporters, either primary active transporters or secondary active transporters in the basolateral membrane, which will then use energy to move the calcium from the intracellular fluid to the basolateral fluid here, and these will now just be located in the basolateral membrane, and it's truly utterly dependent on the fact that these two portions of the membrane are not communicating as far as proteins, integral membrane proteins are concerned. Okay, right, so we're going to have both a primary active transporter and a secondary active transporter which function to move the calcium ions from the intracellular fluid to the basolateral fluid here. And there's not that much space, so I'll put their names over here. So we'll start with the primary active transporter. So the primary active transporter that's going to be involved in moving calcium ions from the intracellular fluid to the basolateral extracellular fluid here is called the PMCA, and if you've ever studied calcium signaling, you'll recognize this protein. Its name stands for the plasma membrane, so the PM is for plasma membrane, and then the CA is for calcium ATPase. Okay, so it's going to be a primary active transporter. It's going to move the calcium up its concentration gradient using energy that it's derived from the hydrolysis of ATP, hence why it's called an ATPase. So the plasma membrane calcium ATPase, and I'll colour it in here in blue. So what it's going to do then is it's going to move one calcium ion out of the cell and into the basolateral fluid, and it's going to also bring in 2 protons every time it does that, and it's also, in order to do that, going to have to hydrolyze a molecule of ATP. It's difficult to put that on there, but you must not forget that the ATP molecule is going to be hydrolyzed as well. So don't look at this and think, oh look, it's just a calcium proton exchanger and the protons moving into the cytoplasm of the cell are what are giving the energy for the calcium to move. No, the protons are there to balance the charge and mean that this isn't electrogenic, but we still are moving the calcium up a massive concentration gradient, and we do need energy to do that, so you do have to hydrolyze a molecule of ATP in order to do that. So, plasma membrane calcium ATPase chucks a calcium ion out, brings in 2 protons every time it does that. That requires a lot of energy because you're moving calcium up a massive concentration gradient, so you're going to have to hydrolyze 1 molecule of ATP every time you do that. Okay, so that's the plasma membrane calcium ATPase. Then we're also going to have another means for extruding calcium from the cytoplasm of this renal tubule cell, but this is going to be an example of secondary active transport. Okay, and this is going to use the sodium gradient across the cell membrane. So this next protein is going to be called the NCX, which stands for sodium calcium exchanger. So the N is for sodium, the C is for calcium, and the X is then for exchanger. Okay, so the NCX is the sodium calcium exchanger, and what this is going to do is it's going to move a molecule of calcium, or a calcium ion, out of the cell in exchange for bringing 3 sodiums in. Okay, so sodium will be moving down its electrochemical gradient because of course sodium is in a higher concentration extracellularly than intracellularly, so bringing the 3 sodium ions into the cell down their electrochemical gradient will provide the energy for moving the calcium ion out of the cell up its electrochemical gradient. So this is therefore an example of secondary active transport. So we have these primary active transporters and these secondary active transporters which are located in the basolateral membrane of the renal tubule cell, which will extrude cytoplasmic calcium brought in by the apical membrane calcium channel here into the basolateral fluid. Okay, and this overall means that we're going to get calcium moving from the apical side to the basolateral side. So we're going to get calcium being resorbed in this transcellular route. So this is the transcellular route for calcium resorption in these renal tubule cells. And this will be occurring in the proximal convoluted tubule renal tubule cells, but it's not responsible for a great amount of the calcium resorption there. Paracellular route is far more important. It will also be occurring in the thick ascending limb of the loop of Henle, where it accounts for about 50% of the calcium resorption that occurs there, and then it will also be occurring in the distal convoluted tubule renal tubule cells, where it accounts for all of the calcium resorption that occurs there. Okay, and it's this transcellular route that is going to be increased by parathyroid hormone. So let's now talk about what parathyroid hormone is going to do. So parathyroid hormone is going to come down to the kidneys and it's going to bind to a receptor that is on the basolateral membrane of the renal tubule cells in the proximal convoluted tubule, in the thick ascending limb of the loop of Henle, and in the distal convoluted tubule. Okay, so on the cell membrane, and I'll just draw the cell membrane here rather than putting it here. Well, actually I will put it there in a moment, but the receptor for parathyroid hormone that mediates most of its physiological actions is a G protein coupled receptor known as the parathyroid hormone 1 receptor, and for short that's abbreviated down to PTH for parathyroid hormone 1 and then R for receptor. Okay, so it's a G protein coupled receptor. So here it is with its characteristic 7 membrane spanning alpha helices. Okay, so this will be on the basolateral membrane of the renal tubule cells in the PCT, the thick ascending limb of the loop of Henle, and the DCT. So I'll just sort of put it in here on my picture. Okay, so what's going to happen then is when parathyroid hormone goes up in the blood, because we have got too low free calcium concentration in the blood, it's going to come down to the kidneys and it's going to bind to the parathyroid hormone 1 receptor on these renal tubule cells in the proximal convoluted tubule, in the thick ascending limb of the loop of Henle, and in the distal convoluted tubule. What is it going to do? It's going to increase the transcellular calcium resorption. And how is it going to do this? Well, it's believed that the intracellular signaling pathways downstream of this parathyroid hormone 1 receptor are going to lead to they're going to affect these apical calcium channels, and they're going to lead to some sort of change to these channels, most likely phosphorylation, which is then going to lead to their open probability going up. Okay, so open probability is a really important concept, so I'll just go over it. So it's often abbreviated to PO, like so P with a subscript O, and this means open probability. Okay, and in the context of ion channels, what this means is if I look at the ion channel at any one moment, so I've got a single ion channel, and I'm going to look at it at any one moment, what is the probability that I find it in the open state, and what is the probability that I find it in the closed state? And this is just effectively the percentage of its time that it spends in the open state versus the closed state. So if the open probability is, let's say, 0.5, then that means it spends approximately half of its time in the open state and half of its time in the closed state. Okay, so very simple concept. So activating the parathyroid hormone 1 receptor on these renal tubule cells here, that's going to activate intracellular signaling pathways, which we won't go through, which are then going to result in modification, a temporary modification, a reversible modification. I think it will be phosphorylation, but don't quote me on that, to these apical calcium channels here. And that modification is then going to result in these apical calcium channels spending more of their time in the open state versus the closed state. So that means that the amount of calcium that's actually going to be conducted from the apical luminal fluid here into the cytoplasm of the cell is going to go up, and that's then going to go across the basolateral membrane through these active transporters and into the basolateral extracellular fluid. So you can see that that's going to result in an increase in the transcellular resorption of calcium. Now, this is particularly effective in the distal convoluted tubule, so of course it's going to have an effect in the proximal convoluted tubule, the thick ascending limb, and the distal convoluted tubule, but it's thought to be particularly an effect in the distal convoluted tubule that is responsible for the increase in calcium resorption transcellularly. And as I say, it will now go up to pretty much resorbing all 100% of the calcium ions that were in the glomerular filtrate, so that you're not throwing any into the urine in this time where we need as much calcium as possible. Okay, so that is the mechanism by which we're going to increase calcium resorption then in the kidneys in response to parathyroid hormone. Now what I want to talk about is how are we going to increase the amount of phosphate that is actually ending up in the urine, i.e. how are we going to decrease phosphate resorption in the kidneys. But I think what we'll do actually is have a break first, and then in the next video we'll move on to discussing how phosphate resorption is going to be decreased.